Okay, and finally, two more little very cute scenarios that involve models with differential equation. So here I'll just skip all the details. So the first of them is the catenary curve. Right? So it is the form assumed by like hanging ropes. A catenary curve is described by a certain differential equation. So here is the differential equation. Notice that this differential equation is, strictly speaking, it is a second order differential equation. But if you introduce a new variable, say, so notice that it doesn't have either x or y itself, right? So in other words, if you introduce a new variable, say u is dy dx, then the left hand side is the second derivative of x, which means it is du dx, and the right hand side is a times square root of 1 plus u square. So we can convert it to a first order differential equation. It is separable, and then you can solve it. So I suggest that you try to solve it to see that you will get the right shape. But the funny fact about the catenary curve is that it is possible to build like a road shaped as a lot of little pieces of the catenary curve, and that on that road a vehicle with squared wheels would roll absolutely evenly. So let me show you a video how it can be done. So notice that although the wheels are square, this tricycle, as it rolls by, it doesn't go up or down. So it rolls absolutely evenly. So, and another very cute little thing that I want to mention is the brachistochrone curve. So let me explain what we are trying to model here first. So imagine that you want to design a slope so that sliding along that slope will be as fast as possible, right? So there could be different shapes. So here you see the furthest from us is a straight line. The closest to us is a piece of a circle, and in between is what is called a brachistochrone curve, because it indeed gives us the fastest sliding. So if you try to model it, so notice that they go like this, and the one that came first is in the middle, right? So the brachistochrone problem is the problem to find the shape of a slide that is going to give the fastest possible time of descent. Assuming perfect sliding, so without any tension, and I like this because the differential equation that you'll get is the only example of a differential equation where the left hand side is not just a derivative, so it is something more complicated. So notice that here dy dx, the whole equation is not solved for dy dx. So in order to solve it, you will have to write it as what do you have to do? You'll have to write dy dx squared equals d over y minus 1, and then we'll have to take the square root. So dy dx is going to be equal, strictly speaking, plus minus, but you can choose whether it is plus or minus depending on how you want it to be oriented. Square root of dy minus d over y minus 1. And then you can solve it again as a separable equation. And you will see that the solution is going to give you an arc of a so-called cycloid. Alright, so that's all I wanted to tell about the models.